Okay, this would be the outline of my talk. System modeling, stochastic models, grid and cloud modeling examples, and big data case study, and then the conclusion, a brief conclusion. Well, system modeling, of course, is a very broad term with many definitions. I'm not going to get into the nitty-gritty of that, but the things that is interest us would be basically helping us to measure important metrics of a real-time system by system modeling, to help us study the impact of modifications on input parameters, and also the analysis of sensitivity of a real system to the variation of a specific input parameter. Also, to help us train engineers and users to better understand the real system. The focus will be on system evaluation. By evaluation, we means methods to get inside and also say something about the effectiveness of the system relative to some measures of interest. And methods to do that would be first of all measurement, meaning doing experimental work on real system per se in order to get those information, which usually is a very time-consuming and expensive effort. Next would be the modeling, and in modeling, simulation would be very helpful, but simulation would also be time-consuming, and there are some limitations, and would be difficult, in particular when the details of systems are enormous. The next method would be analytic modeling, which really means by having a mathematical model to solve the system mathematically and get those information that I just mentioned. It's usually difficult, but if it is possible, it would be very, very valuable. Because by modeling the system mathematically and solving it, if possible, one would get a very deep insight of the behavior of the system. And those insights would be very, very important and valuable. One example that I usually give about the advantage of analytic modeling is in physics, in nuclear experimentation. You know, when you do the experimentation, of course it's time-consuming and it's difficult, but then you have the formula of, Einstein formula of E equal to mc squared. So that's the analytic model, will give you tremendous insight, which will help you to be able to design more advanced nuclear systems. So, analytic modeling is my primary focus in this topic. And then there would be hybrid modeling, a combination of the methods just mentioned. And in analytic modeling, my focus would be mainly on stochastic models. And the models analytically used in this context to basically analyze distributed systems by and large. First is queuing networks, which is very well known in many fields, including high performance computing. Markov processes and Markov theory, Markov chains, Petri nets, and also activity networks. Of course, there are many Petri net type models, including time Petri net, stochastic Petri net, generalized stochastic Petri nets, stochastic reward nets, and also time color Petri nets. Many of these models we will use in some of the case studies that I just will come to them shortly. Activity networks, there will be other types of activity networks which we have used so far, so-called time activity networks, probabilistic activity networks, and stochastic activity networks. The application, the case study that I will report would be mainly in grid and cloud environment, as we will see shortly. The report would be really a summary of some of the research results we have recently come up. So, in the first would be the overview of some of the results we published recently in these journals that you see. IEEE Transaction Dependable and Secure Computing in 2015, and in Information Sciences in 2017 to be published. And also IEEE Transaction and Industrial Informatics, which are a paper under review. The first effort was in performability evaluation of grid environment using stochastic rewardings. Now, by performability, we mean performance and dependability. Not only performance, but also the dependability aspect of the system is of high interest. And in this paper, this work, we have done the modeling of a single grid resource using SRN, failure revert behavior of processors inside the resource. We also considered both local and grid tasks in resource, and studied 3 different task dispatching policies. Performance measures of interest in this work has been mean number of waiting grid tasks, blocking probability of grid tasks arrivals, mean response time of grid tasks, and the dispatching policies. 3 policies were considered: without priority, with higher execution priority of local tasks over grid tasks, and with higher execution priority of local tasks over grid tasks, preemptive priority. The last one was non-preemptive. So we used RewardNet to model the system. So this is a model of the system. I'm not going to get into the details of the model, just because of the constraint of time. So that was policy 1 and policy 3. We did the evaluation using analytic models and also simulation. So you see the results comparable results for policy 1, policy 2, policy 3. For MWT, probability of blocking, and MRT, mean response time. As you see, the simulation results and the analytic results are very, very close. As I will explain later, simulation was time consuming, but analytic model was very fast. I'll show it, report it in shortly. We did the aggregation of single models to capture the entire environment. So there was two modeling approach, monolithic, in terms of analytic models. We got the Markov chain of it. It's a huge Markov chain in many, many states. We did folded model, be able to shrink the number of states in the Markov chain. So these are all in analytic modeling context. And also the last method, which was very successful, was using so-called fixed point approach, which drastically decreased the number of states in the Markov chain in order to solve it analytically. And we use that one to do the analytic results, report the analytic results. So the number of nodes, 2, 3, and 4, you see the results for those three analytic modeling methods are very, very close for the measures of performance, three measures of performance that I just mentioned. The number of states of the underlying Markov chains which were resolved, on the other hand, you see, for example, when the number of nodes increases to 4, for the monolithic method would be almost 1 million state. For the folded one, 30,000. But for fixed point, less than 1,000. So it would be much easier to solve a Markov chain. It's less than 1,000 state than around 1 million. So the Markov chain matrices, the resulting Markov chain matrices for example, for the case of 4 nodes would be more than 10 million, the non-zero elements of the matrix. But the folded one would be 500,000, and the for fixed point would be around 3,000. Drastically decrease. So that was one example of the modeling, analytic modeling example in the context of grid. Another one was the performance and power modeling and evaluation of virtualized servers in gas clouds. We did the modeling on gas cloud using sand, another modeling method that I just mentioned. And we did modeling of DVFS, dynamic voltage and frequency escape, and we showed the impact of that. And also we studied homogeneous virtual machines on servers and considered different workloads in day and night. So this was the model of the system under consideration. That's the SAM model of the system. Again, I'm not getting into the details of the modeling, features and constructs. And the measures of interest were blocking probability arriving request, instant service probability, mean waiting time, throughput, mean response time, and power consumption. Comparing the power consumption of a non-virtualized system with our considered system, which has been modeled by SAM, without virtualize and WIP, you see the improvement. So the evaluation has been done by SAM, analytically. And the DVFS, again, we see the improvement in terms of throughput and also decrease of power consumption. And again, the evaluation have been done analytically using SAM. The third effort in this regard was modeling and evaluation of service composition in commercial multi-cloud, this time using TCPM, time-colored petrolets. In a multi-cloud environment, multiple user and different complex services being used. We modeled the cloud federation, consider different numbers of services with various QoS in a cloud, measure the mean response time and dropping probability of complex service requests, and finally, we minimize the number of clouds involved in providing a complex service. So that is the model. So this is modeling the same system using TCPM. And we did solve this model analytically using TCPM, but then compare it by simulation using CloudSim. I showed really the error was very, very negligible. The scenario is 3 clouds and 5 services, one case, and the second scenario was a bigger cloud with 10 clouds and 15 different services, and these are the result. Convergence of the mean response time to the steady state value in the first scenario. So the blue one is the result we got using TCPM model, was very quick. The other one, the red one, is by using CloudSim, which of course was very time consuming. But as you see, errors, they're getting almost the same result, indicating almost the same results. This is for the second scenario. Again, we see in particular in a steady state, almost the same result, using analytic modeling as well as simulation by CloudSim. Again, the mean response time in seconds and dropping probability shows very, very close results and small errors for both TCPM model as well as by simulation using CloudSim. So again, this is the result of the second scenario. So what we conclude in this case is, although the result of TCPM and CloudSim are very close to each other, the time required to reach the steady state results are very, very different. For example, in an experiment with 100,000 potential users, in the second scenario, time to solve TCPM was 2 minutes, while using CloudSim was 97 minutes. When we increase the size of the system to 1 million potential users, time to solve TCPM is about 10 minutes, while CloudSim, it takes 12 hours to get the same result. So it shows the advantage of analytic modeling. The last one, a brief presentation of our research in big data is this paper under preparation, and we are sending it to ITB Transactional Cloud Computing soon. Concern of every data-intensive business, of course, the big size of data and bottom line issues, $122 billion. Challenges, processing and storage. Volume velocity and variability, conventional DPS incapable of handling. And it requires new approach and tools. Also in evaluation, not only in design, also in evaluation. They have considered MapReduce, Hadoop, Spark, and so forth. You know, MapReduce is a dominant programming paradigm. Hadoop, widely used open source implementation, other layers and extensions, Hadoop distributed file system, and Yarn and Tez, which usually has complex workflows of several MR stages. About 190 configuration parameters, measures of performance of interest we have focused were throughput, availability, reliability. Although availability and reliability could be considered as dependability measures. So we did a performance evaluation in order to answer how good the configuration is. Modeling formalism being used was SAN, Stochastic Activity Networks. And the tool to solve SAN was Mobius, which is a very popular tool developed in the University of Illinois at Urbana-Champaign under the leadership of Professor William Sanders, a colleague of mine. Solver, iterative steady state solver. Composite modeling, we use that feature and in order to share places among, by sharing so-called places in SAN among various submodels. These are the features incorporated in Mobius. Mobius would support them. So, big data MapReduce, that was the model of SAN, SAN model of the same system. Another one was Tez. And this is the corresponding SAN model. So this is monolithic model, composite model. We use Mobius, the tool, which support this composite modeling to solve the system analytically. Validation, we did it with measurement. And the measurement was done in Deep C, Dependable, Evolvable, Pervasive Software Engineering Center of Dr. Danilo Ardanga, professor at Politecnico di Milano, Italy. So we did the measurement there. Cluster setup, MapReduce queries on Synercom, Italian Supercomputing Center, Tez queries on Flexion Public Cloud, and the number of virtual machine 30, 120 processor unit, and 240 container. So we did model this. These are the results. And then we, using SAN, solving the system analytically. The result came out very quickly using Mobius. And then we compare it with the measurement, as I mentioned. And the error were, as you see the last column, acceptable, very low. Again, by experiment and model. Experimentation, as I mentioned, was the measurement. So that would be the blue curve. Modeling using SAN, solved by Mobius, very quickly, you see the result in red. Results are very, very close. The error, as you see the last column, is quite acceptable in terms of percentage. Test model validation also indicate the same thing, the same trend. MR model, the average error was 6.3%. Test model was 7.9%. The accuracy of the model was, I would say, very good. Multiple parallel queries, state space explosion, state space reduction techniques. These are the research for the future. And conclusion, experiment in many systems, including high-performance computing, supports our conclusion, the same conclusion. Experiment is valuable, but very, very costly usually. Sometimes impossible due to the circumstances. Simulation could capture the details, but would be very time-consuming. Analytic modeling, in particular if it is accurate, would be excellent. We show that by analytically solving the system, we could get to a very acceptable accuracy, low runtime, and not only that, as I mentioned, more insight about how the system behaves. Compare E equal to MC of Einstein with the experimentation of the test of a nuclear bomb or whatever. They are trying to do, the aim is the same, to design a better system. But the theory, the mathematical work is very valuable because it gives you insight about the system. Then you could come up with some other more intelligent design of the system in the future. So that's the advantage of analytic modeling. Not only that, as we see, it gives you quite accurate result very fast too. So that concludes my presentation. Thank you for your attention.
May you take questions? Professor.
I'm very afraid of Dr. Rouhani because he said, I'm going to ask you. I said, well, if you ask a question, I will be trouble.
Any questions? No?
Dr. Rouhani, please. No.
Why not?
Well, this is good for him. That's why. Okay.
Okay, I'm not allowed to ask you.
That's even worse.
No, I just wanted to clear myself.
Sure.
You argued for analytical modeling, giving the evidence that simulation takes more resources and more time. Isn't it the fact that analytical modeling takes more human brain resource than simulation or than real experimentation?
You are exactly right, sir. Very important point. Again, I get back to the same example. I'm sure only Einstein could
Come on, people.
and it was not easy for him. I'm sure he spent years to come up with that theory and that formula to explain the behavior. But then it has revolutionized, and it is still revolutionizing the technique of designing more designs in the nuclear era. But experimentation, of course, is costly. Doesn't need that much brain. Some of the military people, and you just takes money and effort, and you do it. And of course, the result is very important because it really means that that's the real results. So both are important.
Okay.
But
So it's a trade.
but the analytical model is mathematical. So that's why is mathematics so important in engineering? Because it is. So that's the same issue.
It is, but it's hard. It's not as simple as you say. Okay. Thanks very much indeed.
Thank you.
Our next speaker is not available physically,